Look up at the night sky and you're looking at a trap. The distances between those stars are so vast that trying to cross them in a straight line is essentially a physical impossibility. Even if we boarded our fastest modern spacecraft and aimed it at our closest stellar neighbor, Proxima Centauri, the journey would take tens of thousands of years. To reach these worlds within a human lifetime, we cannot move through space. We have to figure out a way to step around it. Exploring the galaxy requires a shift in how we view the void. Instead of seeing space as a distance to endure, we have to treat it as a material that can be manipulated and shortened. In 1935, Albert Einstein and Nathan Rosen discovered a loophole in the equations of general relativity. To visualize this, physicists use a technique called embedding. If you treat the universe as a flat sheet, you can bend that sheet through a higher dimension until two distant points touch. This creates a throat-linking, distinct regions of spacetime. Step into one end and emerge light years away via a cosmic shortcut. In Einstein's universe, gravity is the force that dictates this geometry. The more mass you concentrate in one spot, the more space curves around it. To create a curve sharp enough to fold space back on itself, you need an object of extreme density, a black hole. This requirement creates a practical crisis. While the mathematics allows a space-time tunnel to exist, requiring a traveler to enter a natural black hole suggests that any journey would end in total destruction. The first major obstacle to traversing a black hole involves tidal forces, the violent gravitational stretching that occurs near massive objects. Most stellar black holes are surprisingly small. When a massive star collapses, it can pack several solar masses into a radius of only about 30 kilometers. This tiny radius creates a lethal gravitational gradient. The pull on your feet would be so much stronger than the pull on your head that any ship would be torn into its constituent atoms thousands of kilometers before it reached the entrance. Even if you survived the gravity of a larger black hole, the tunnel itself is doomed. A standard, non-rotating wormhole is unstable. Its gravity causes it to instantly snap shut. This happens because the central singularity exerts an infinite gravitational field. The tunnel is strangled in the middle before light or a spacecraft can cross it. Standard general relativity suggests that any natural wormhole created by a collapsing star will either shred matter or crush it, making travel impossible. To find a traversable path, we have to look at rotating black holes. In the real universe, nearly everything spins, and a rotating black hole follows a more complex geometry called the Kerr metric. Centrifugal forces stretch the deadly central singularity into a ring shape. This allows a trajectory where a traveler could come safely within a hair's breadth of the singularity, passing through the ring to emerge in another region of space. While the ring provides a physical opening, the problem of the collapsing walls remains. The throat of the wormhole still lacks the internal strength to stay open. In 1988, physicist Kip Thorne proposed a requirement for traversability: exotic matter. Exotic matter exerts a repulsive tension called negative pressure. By lacing the wormhole with this energy, you could prop the throat open. Quantum mechanics suggests this is possible through the Casimir effect, which creates negative energy states in a vacuum. This quantum breakthrough shifts the focus of the problem. The hurdle moves from the rigid limitations of classical gravity to the immense difficulty of material engineering at the quantum scale. These requirements confirm that a traversable wormhole is not something that occurs randomly in nature. It must be an artificial structure, engineered with precision. The energy required is staggering. Stabilizing a wormhole large enough for a ship would require an amount of negative energy equal to the total output of our sun over an entire year. An advanced civilization might achieve this by capturing a microscopic wormhole from the quantum fluctuations of spacetime and inflating it to a macroscopic size using this massive energy. The manufactured shortcut depicted in films like Interstellar follows a rigorous mathematical framework. It represents a blueprint for any civilization that gains the power to manipulate energy on a stellar scale.